Hello everyone, June 16th. Alright, a little bit late today. Well, let's do it. Count the number of arrays with k matching adjacent elements. Count the number of arrays with k matching adjacent elements. You're given three integers, n, m, k. A good array of size n is defined as follows. Each element in an array is in the inclusive range 1 to m. Exactly k indices I, where I is from 1 to n, satisfies the condition array I minus 1 equal to array I, or to the number of good arrays that can be formed. Apparently I solved in the past, so let's try to get this one again. So we have n element. So the first one I have three elements. Okay, I have 1, 2, 3 elements, and each one is from 1 to 2. And what we want is exactly k indices satisfies. So k numbers has to be this. K of I, actually k plus 1, right? When you have k plus 1 consecutive. So in this case, k equal to 1, so I need to have 2. That's the same. The number of good arrays that can be formed. Good arrays, yeah, like I have, like these two is the same. These two are the same. So if these two are the same, I can do 1 or 2, right? So we have to do 1, 1, 2, right? And then 1, 2, 2. And then 2, 2, 1. And then 2, 1, 1. Right? So here, k equal to 2, so I need 3. So I total have 4. So 1, 2, 3. So I have 3. So I have 1 and 2. There are only 2 different ways to go. And each one I need m equals 2. So I have 3 options. No, I have 2 options, 1 or 2, right? So basically, I have, wait a second, this one is exactly k indices, where I minus 1 is equal to I. So I have 1, so I have 1 and 2. Oh, it doesn't have to be consecutive. It's just pairs. It just pairs, right? It just pairs. So I need to have k pairs. So this is like 2 pairs. So I can have this pair, this pair, this pair. Right? I have 3. So pair-wise, I have 1, 2, 3, 4. So I have 3 pairs possible, right? And I can choose how we want these 3 pairs, right? I can do this and this. This is one option. And then, or I can have the pairs like this pair and this pair. Okay, let me think about it again. 1, 2, 3. Right, so I can have this pair and this pair, or this pair and this pair, or this pair and this pair. Basically, I have these 3, right? And we can pick and choose. So does that cost like 3 choose 2? Because I need to pick 2. Right? I have 3 positions, I got 2. And for each one of them, right, I have 2 options. Right? For each one of them, I have two options because they have to be the same, and the remaining just need to be another number, and the remaining positions. Ooh, it depends. It depends on how we do it. Like if we do this and this, depends if they're the same. Like if there's an overlap. If there's overlap, then I see there are a lot of different ways to do this. Like you can have overlap and then you can have no overlap. But essentially, yes, you have an array, right? Doesn't matter, you can throw your numbers in, you can throw your i's in. It can be like this, which is totally fine. You can pick whatever, right? You can pick whatever. It is after you take your pick and you can fill it in with whatever number. But each one will have like different. Yeah, it depends on if they overlap. If they overlap, then they have to be the same. How do I solve that? DP this? I can't think of the math. Like the previous submission says mathematic ways, but I couldn't figure out a mathematical way to do this. I saw it in January this year. I can't think of a mathematical way to do this. If we do DP, we can say if I want the first one to match, okay? If I want a first one to match, then what I want is I can have this one either matching. Like if I have this one match, if this one does not match, right? Then the answer is finding. So we can say, I don't know. How big is K? That seems to be very big. So you have to go from every single one. Because it'd be like DP from I to the end with J remaining pairs, right? So if you're here, if these two not matching, and you can find out how many different ways to get them not matching, then it will be just dpi plus 1j, right? It's just dpi plus 1j. If these two are matching, you can also find out how many ways, and it will be starting from here, right? So it'll be dpi plus 1, j minus 1. But with a requirement, because you start from here, and these two are the same. So you start from here, right? And when they match, if you want to match, they have to be the same, right? Or you say you don't want them to match, then it will be a different. So we have to have another one. Like, do we match the previous? So if these two do not match, then we move on here. These two do not match, right? And we go from here to the end. And these two already don't match. Well, actually, we should go from here, right? Start from, no, it's from here. But we have a number, we have something here already. Now it is from here towards the end, and I decided not to match, so whatever this number gives me, right, whatever this number gives me, because I don't match, so I can just times, because whatever this number is, so they'll give me like say 100 different ways, and then for each way I can find n minus 1 way to do this, right? So this, if these two are matching, right, if these two are matching, then start from here. I'll do I plus 1 j minus 1, right? I'll do that number, and for each one that will only have 1. So basically it's going to be m minus 1, right? It'll be these two plus this plus this. So dpi j will equal to dpi plus 1 j times n minus 1 plus dpi plus 1 j minus 1, right? So if I do a, like this, this is I, this is j. So dpij, let's say we do here, is equal to I plus 1 j is this, and I plus 1 j minus 1. So this equal to these two. So this equal to these two, this equal to these two, this equal to these two. Which means if I fill out the bottom layer, right? I fill out the bottom layer, and then we go from here. This give me this. This give me this. This give me this. So another way, I need to fill out the bottom layer first. What's the bottom layer? Bottom layer is I is the end, right? I is the end, so it was the end. And isn't that always going to be 0? Right? So this is, let's use this as an example. Right? Let's use this as an example. N equal to 4. Right? So n equal to 4, which means we have 4 rows. And k equal to 2. Right? So I have 1, 2, 3, 4 rows. K equal to 2. So we say, how many left? So 0, 1, 2. Right? So this is j. I have 0, 1, 2. I is 0, 1, 2, 3. So when we have the last one, right? When we have the last one, 1, 2, 3. When we have the last one, we want to find, starting from here, right, with 0, how many ways do we have? Well, m equal 2, so there's like 2 ways, because this is saying 0 pairs, right? And then we have 1 pairs, we have 2 pairs. So now start from here. So this will equal to this times n minus 1. N minus 1 is always 1. So that's a 0 plus a 0. Here, it will be this plus, it will be actually 2. This is going to be 0 because, actually, wait, hold a second. This is going to be, this times 1, so it's 2. 2 plus 0 would be 2. Really? 2. We're talking about starting from here, right? With 0 pairs. With 0 pairs. With 0 pairs. So 1, 2, 2, 1. Right? Okay. So here, that's going to be 2. This is going to be 2 plus 2 is going to be 4. This is still going to be 2. And here is, this is going to be 6. This is going to be 6. And this is still going to be 2. What we want to find is dp start from 0, giving me 2. So 0, 2. So the answer is 6. Oh, I think it works. So for this one, I have n equal to 3. Okay. So again, so this will be 2, this will be 0. So n minus 1 is 1. So this is going to be 2, this is going to be 2, this is going to be 4, this is going to be, that's it. Then we get 4. So it is going to be this is k, so n times k. I feel that's going to time out. Right? That seems to be timeout. Hold on, maybe we can do better. I don't know. I mean, I feel like it's gonna time out because we have to go through every single. Have to do this. Have to do this. Have to do this. Have to do this. Right. So the first is definitely all gonna be like this. Right. That's the first row. And starting from here, but we have to go through. Huh. So like this is all gonna be 0 until here, right? Yeah. It's gonna be like this. Because these are gonna be 0. Yeah, these are all gonna be 0. Really? These are all gonna be 0? Oh, of course, because this is, it's not gonna, it has to be smaller. K has to be smaller than n. So yes, of course. Diagonal, right? Diagonal. So yeah, these we don't have to consider. So n minus 1. So it's 1, 2, 3, 4, 1, 2, 3. So yeah, these we don't have to consider. Right? So this is a given. Now we just want to know what this number is. Now to know what this number is, we need to know this number, right? And to know this number, we need to know this number. So we can do diagonal, right? And of course we can get really fat, really slim, right? So we do really slim. Yeah, let's maybe try this. So I get into 0, 0, and then we fill it out. Then we need to fill out this, and then fill out this. So this depends on these two. And I believe these are all 2's. Right? These are all 2's. So we need to fill here. Right? We need to fill here, fill here, fill here, fill here, fill here, and then fill here. So it's like going this way, and then this way. So here, right, what's this value? This value is 2 times n minus 1 plus 2. That's this. Okay. what's this value? This value is, actually we probably can do it. Hold on, let me remove all this. Ugh. Right, here is 2 times n minus 1 plus 2. And this will be this, right? So it will be 2 times n minus 1 plus 2 times n plus 1 plus 2. Okay? Which means this is going to be, so yeah, so this, so this is going to be 2 times n minus 1 plus 2, which is 2m. This is going to be 2m times n minus 1 plus 2, which is equal to 2m squared minus 2m plus 2. Right? Well, I think it'll be easier if we don't do it. We can call n minus 1 something else, which is fine. Right? So basically this times n minus 1, so 2 times n minus 1 squared plus 2 times n minus 1 plus 2. Right? And this is 2 times minus 1 tripled n minus 1 squared plus 2 times minus 1 plus 2. Right? So here is, actually we can get 2 out. It's just n minus 1, 4, n minus 1, 3, all the way to 1. That's this value. Right? And then we can compute this row as well. Right? So like here, what's this? This is 2 times n minus 1 plus 2 times n minus 1 plus 2. What's this? So this is essentially 4. Right? This is going to be 4 n minus 1 squared. Oof. Wait, hold a second. This is going to be this plus 2 times minus 1 plus, Alright, this is getting a little more complicated. Like this row I can handle. This row, feel like it gotta be a better way, right? It gotta be a better way. Yeah, the constraint, they didn't really say the constraints are n times k, so that's what worries me. Because k can be big. I mean, if k can be big, now here's the thing, if k is big, hold on. Again, if we have 1, 2, 3, 4, I have 5 on the end, so k can only be 4, right? K can be 0, 1, 2, 3, 4. So k can be 0, 1, 2, 3, 4. Right? N can be 1, 2, 3, 4, 5. And essentially it's the same thing. And here is the same. Right? The bottom row is going to be 2. This one all going to be 2. And then we just need to figure out this. And we know diagonal is going to be 2. So in this case, yeah, if k is equal to n minus 1, it's going to be this one as well. And as k gets smaller, right, we can always prepare this, so we just need to figure out all these numbers. Like if k is here, then we can just compute everything, right? We can compute everything here, and these are all zeros. But how do we compute these fast? Like I can do this, I can do this, I can do this, right? But then I have to compute this. I mean, it's the same thing because this one we can already compute directly. So here it's the same because we are doing the same thing, right? It's still like for each one it's going to be, 2 times m minus 1 plus, dp, in this case, let's call it 3, 1. But we can calculate what this 3, 1 is immediately, right? So this is like here. And then we do, 2 times n minus 1 squared plus, dp3 1 times m minus 1 plus dp2 1. See, that is not something I think is doable though. Because the value plus is not. I don't know. What did I do? I don't know what this is. How many independent entities a good array for each index marked by k must have the same value as index minus 1? Thus, find out how many independent entities a good array has. index marked by k and must have the same value as index minus 1. Two elements form an independent entity. If another index marked by k is placed immediately after the previous index, then our entity has three elements. Consider any placement of indices. We can see that no matter how we move the indices around, the total number of entities remain the same, which is n minus k. This is because if we move one index to another location, its original location does not lose an entity, and the new location does not gain an entity. Sequentially, the first entity has m different choices. The remaining entities have n minus 1 choices. Then the k indices can be placed in any combination in n minus 1 positions. With these two pieces of information, we have a solution. Okay, I don't understand anything that I wrote. How many independent entities a good array has? For each index marked by k, it must have the same value as index minus 1. Thus, we say these two elements form an independent entity. Okay, that's independent entity. If another index marked by k is placed immediately after the previous index, then our entity has three elements. Okay, so these are independent entities. Now we consider any placement of indices. We can see that no matter how we move the indices around, the total number of entities remain the same. The total number of entities remain the same. I seem to remember this insight. Wait, how does that consider? We can see that no matter how we move the indices around, the total number of entities remain the same, which is n minus k. If we move one index to another location, its original does not lose an entity and the new location does not gain an entity. Huh? What does it mean? What does this mean? So we have two entities. Oh, that's two entities. Oh, consecutive. I can just say consecutives are one entity. So what we're saying is we want to have k of them, right? So we have k of them in an array, and each will form entity, and this will form an entity, this will form an entity, this will form an entity. And once we're done, if those are not, if we have like, so you have k independent entities, which means they don't overlap. So we take k positions, right? And take k positions. Yeah, so if we take k positions, so the remainder is n minus 2k, if there's no overlap. N minus 2k, that's the remainder position, right? They all are independent entities. And then plus the k entities, so we have n minus k entities. Yes, right, n minus k entities. Now if they start to overlap, okay, if they start to overlap, now we have some overlap. So we start overlap, that means we start merging some of this, right? So imagine we have no overlap initially. Now we are overlapping, so let's say these overlap. So when they overlap, we lose. So these two become one entity. So we lose an entity for them, right? Because initially we have, let's say, 3 entities. Now we have 2 entities. Now we have 2 entities. And then for them, I also lose one. Wait a second. Hold on. Let me do it again. So let's say n equal to, I don't know, so let's just say we have n, we have 3 entities. Okay, so k equal to 3. So initially I have n minus 3 entities. So yeah, we can just use this n equal to whatever n equal to. And I just call this as 1, 2, 3, 4, 5, 6, 7. Yeah, we have 4 in between, right? We have 4 in between, and we have these. That's the original. Now if these two get merged, right? If these two gets merged, so I'm losing an entity here, right? Because now, say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. N equal to 10. So initially I have 7 entities. Okay? 1, 2, 3, 4, 5, 6, 7. So now, what if I have still this one, and then we have a 3. Alright, now we have this. Now we have these 2. Got this. We got this and this. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right, we still have 3. We have 1, 2, and 3. So the total entity is 1, 2, 3, 4, 5, 6, 7. It's the same. Why? Because when we merge these two, right, when we merge these two, so this, so initially we have 4, right? Now we have 3. And then we're losing one entity. But because the merging, I actually add one entity. So the total entity number is the same. Yeah, so we have 2 entity and a 3 entity. Now as we move in once, this entity comes here, right? And then I'm moving 1, and we add a new entity. So that's why it's the same. So basically what we're saying is when we merge the 2, right? When we merge 2 in together, the action of merging creates, imagine the original position. The action of merging creates 2 empty space, which means we create essentially 2, right? We create 2 new entities, but at the same time, we're losing. Yeah, we can also think about like just swapping, right? We move this closer, so we just swap, swap, swap. So when we have something like this, it's the same as this. And then we merge, so we're losing one entity, but then we gain an entity. So overall, the total number of entities is always n minus k. So each entity can contain only one number. So what we have is n minus k, n minus k number of entities n minus k number of entities, but we can choose. No, they all have to be. Shouldn't they all be different? Yeah, they should all be different, right? N minus k entities. They should all be different. Which means I still don't understand. The first entity has m different choices. Okay. The remaining entities all have m minus 1 choices. That makes more sense. The first entity has m choices, and this is m minus 1, everyone. So it's going to be, but you also need to know how to position the n minus k entities, because you have different ways to position them. N minus k entity essentially means, because it doesn't matter, it's just n minus k, n minus k indices. So we can say n minus 1 n minus 1 choose, because you cannot choose the first one. If you consider this as the thing. So it becomes n minus 1 among these choose n minus k minus 1. Choose 6 of them. Really? Choose 6? Okay, I don't understand. N minus 1 choose k. Okay, n minus 1 choose k is just different k positions, because the k position I cannot include this. So that's n minus choose k. That's what they can be, right? That's what these things can be. Now once these things are settled, right? Once these are settled, then what? Then for each one of them, there must be n minus k entities after we're done. And the first one, so basically it's n minus 1 choose k. That's the total number of ways the k indices can be. And then for each one of them, I have m times m minus 1, n minus 1. So it's like this. M times power m minus 1, 2, and then times combination mod. Ah, now it makes sense now. How do I do math combination? You're shitting me. I don't have a... Oh. I can't do it. Alright, I think it's just unnecessary. I'm gonna Python this thing. I'm gonna Python this thing. Mainly because I'm just too lazy to. Okay. Well, we'll do it. It just, but still, it's gonna. We will mod every single time. Okay. We'll mod every single time. Like factor. Oh, we cannot mod every single time, can we? I don't know. Alright, let's see how to do it in C++. Combination, factorial. Oh, inverse factorial. I seem to remember something vaguely similar to this. Oh, inverse factorial. I think this is for... Yes, inverse factorial. How do you get inverse factorial? I forgot. Inverse factorial. Okay, this is factorial. Inverse factorial. Oh, yes, there is something like that. Inverse factorial. You do the power thing. Mod minus 2. modulo inverse for division. Modulo inverse. I don't remember modulo inverse. Oh yes, it's Fermat's little theorem. Fermat's little theorem. Yes. P minus 2. P minus 2. A to the P minus 2. If A mod P is equal to 1, then this and this mod P has the same. Which means if I want to find this mod P, I just need to find A to the P minus 2 mod P, right? Which is essentially what this do. This is A to the mod this, is the inverse factorial of some stuff, and that's why you have to do this mod P, right? Have to do this mod P, which basically just this factorial divided by this factorial. It's this. This factorial, n factorial divided by m factorial. How do I do that? I cannot do division. What I can do is a factorial times m inverse m factorial, not inverse m factorial mod p, like this. Basically this mod p has the same value as this mod p, right? And then you multiply these together, and then you do this together. Makes sense. Makes sense, but makes sense doesn't mean that I'm going to do it. It just means I am still going to use 6, that's 7, right? What? I thought I copied. Oh shoot. Oh Jesus. I'll have to move to 2026. My God. Alright, I'm gonna copy again. Yeah, this is not right. It's 2025. It has to be 2025. There you go. Okay. Let's do this. Yeah, we didn't do it. I read the solution. I am not in a good shape today to do this. This is what? 34, 5. I'm surprised I solved it last time. Yeah, I'm surprised that I solved this last time in January. January the 6th, 5th actually, 2025. I am not able to solve it again today. So the ideal is that, okay, whatever k indices that we choose, there will always be n minus k number of distinct, right? Number of distinct, not distinct, independent entities. An entity is a consecutive subarray. Is a consecutive subarray. Well, subarray is consecutive, so I don't have to use consecutive. It's a subarray, right, consisting of the same value, right? Consisting of the same value, right? The extreme case is that all k pairs, none of the k pairs, is that none of the k pairs overlap, right? Thus, we have n minus 2 times k plus k equal to n minus k independent entities, right? Now, if we allow some pair to overlap, right? When one index is overlapped, we when overlap happens, right? When overlap happens, we lose one entity from a pair, right? From the pairs, but we also gain an entity from the overlapped index, right? Overlapped index. Thus, the total number of independent entities remain the same. So now, okay, so that is done. So we also know, right? We also know that there are n minus 1 choose k, right? Number of ways to place the k indices. We cannot put k at position 0. And for each way, we have m choices for the first position, and m minus 1 ways for each of the remaining n minus k minus 1 entities, right? Simply n minus 1 minus, just double check, it's n minus 1 minus 1. Yes, yeah. For the remaining n minus k minus 1 entities. Thus, the solution is m times m minus 1 to the power of n minus k minus 1. That's an n times n minus 1 choose k. Right, so combination is math.com n minus 1 choose k mod and we'll return m times power n minus 1 to the power of this mod equal to mod times combination and the mod. Yeah, I don't have time to do the Fermat's theorem. guess it took a long time to figure out what it means. Maybe we'll feel good enough to implement the other way, but that's it. That's pretty bad. Ah, but we did this one yesterday, so we can deal with this. Alright, that'll be it. That was bad, but it's okay. I'll see you guys tomorrow. Adios.